Hello, I'm Sophia, and this is the second paper I'm analysing for the third assignment of Complex 529. This paper is authored by Jhonny Mertz and Ingrid Nunes, and in it they're exploring this novel approach for software monitoring. So a lot of our context about this is that monitoring is a very important component of almost any software system. It allows developers to gain insight into how the system's functioning and can provide useful information when things go wrong. Particularly in a production environment where we don't have sort of a live debugger running. But the issue with this is that monitoring doesn't come for free. There's an execution overhead associated with producing logs, transporting them, and then processing them. And in some contexts like embedded systems or real-time applications such as high-frequency trading, this overhead can actually have a significant impact on the usefulness of the system. And so this is a particularly large problem when we start thinking about self-adaptive systems. The very first component of the MAPE-K model is monitoring. And intuitively we can sort of realize that it's impossible for a system to adapt itself effectively if it's incapable of measuring itself and comparing it to its environment and its goals. And so we run into two big problems here. Firstly, the overhead of monitoring can potentially be quite expensive, and we've already covered that. But secondly, that overhead actually changes the observed behavior of the system. So for instance, by adding this extra execution overhead for monitoring, we may have inadvertently increased the amount of time it takes for us to service consumers of our system, and that's going to have a run-on effect throughout our control loop. And so for most developers, they don't really need to worry about this so much. If you're building a standard CRUD app, then your instrumentation overhead doesn't really matter so much relative to your other concerns. And so because of that, there's a lack of research in this space outside of very specific applications like profiling a program for memory leaks or fuzzing. There just hasn't really been all that much investigation into a generalizable approach to monitoring as a problem. And then finally, the problem only scales up over time because as software projects become more and more complicated, it becomes much harder to develop methods for monitoring them effectively. And so we're at this point where we don't really have a particularly great solution. So there are some fairly naive approaches. We have the most popular approach, which is sample-based monitoring. And sample-based monitoring doesn't really do anything terribly intelligent. You produce your execution samples as normal, and then you discard some random proportion of them. And so over here I have an example of some code hooking up to the Sentry API. Sentry is a SaaS app for application monitoring. It sort of records things like error traces and performance metrics. And it has this configuration parameter here, traces sample rate, and when it's 1.0, all of the traces will be recorded, and if it's 0.5, then only half of the traces will be recorded, etc., etc. But sample-based monitoring has some issues because as it's totally random, we might wind up producing traces which aren't actually representative of our underlying system. So we've got a slightly more complicated approach called stratified monitoring, and what stratified monitoring does is we categorize our individual traces into categories or strata, and then the sampler will ensure that the proportion of each category being sent off to our monitoring service is the same as the proportion of those categories which we're actually producing within our system, so it's a bit more representative of the system. Now the author of this paper has quite a different approach. There's this two-phase approach to monitoring which they propose. We've got a coarse phase and a fine phase. So the coarse phase is responsible for collecting very high-level statistics about the underlying system. This is things like how many times an individual method has been called, the responsiveness of the method, changeability in terms of what's coming out of it, etc. These are quite cheap to measure and the overhead's not so bad. And these statistics are used in tandem with user configurable relevance criteria in order to filter the methods into relevant methods and irrelevant methods. And the relevant methods are subject to this fine-grained monitoring where more traditional, detailed, heavy execution traces are generated. And this process occurs in real time. Our relevant methods can sort of come in and out of the set as the system evolves. The other thing to keep in mind here is that we can still compose this with another sampling strategy. So this diagram has a sampling strategy item here. So we could still do stratified sampling if we needed to further reduce our monitoring overhead beyond what this does. And so this is a little better than the naive approaches we covered earlier because the methods we're including in our monitoring are actually guided by the system's behavior in real time, as opposed to being defined statically. So you might have, another way you can do it is you pass in an environment variable which turns on or off different components from being monitored, and that's quite bad because it's static and it doesn't sort of evolve over time. We've also got the ability to implement a sliding level of granularity here. So in the paper, they're only talking about filtering methods into irrelevant and relevant baskets. But the way that's done is through a numerical relevancy score, which is sort of linked to those relevance criteria that the user specifies. And so it's easy to sort of imagine an extension to this approach where instead of having two buckets, you have a third bucket in between relevant and irrelevant, where you don't produce full execution traces, but you produce a cut down version of them. And the last thing is that it's very user tunable. The user is able to specify the relevance criteria that they're interested in, and these are qualitative criteria about the way in which the user expects the system to operate. So it's been evaluated experimentally. Mertz has another paper in which he describes a software component called APL cache. And APL cache is an automated software caching tool which functions by monitoring the inputs and outputs of methods within some underlying program and using that information to automatically identify caching opportunities. You can read a little bit more about this system in the citations paper. And so for this evaluation, the monitoring component of APL cache has been swapped out with this two-phase approach. And they've run through the same scenarios that they ran through in the original APL cache paper in order to get an apples-to-apples comparison between the two monitoring approaches. And overall, the results are actually quite positive. So we can see here an excerpt of the results from this experiment, and we can see that in this column here, my mic cut out. You can see in this column here that the throughput of every single case has improved over baseline, which is good. This does come at the cost of missing some cacheable opportunities, however. And this is because the two-phase approach isn't comprehensively monitoring the system as the original monitoring system does. There's no sort of distinction between relevant and irrelevant methods. And the other thing to keep in mind is that the performance for the Shopweiser application doesn't seem to be quite so good as the rest of them. We can see that our hit rate is relatively low compared to the other experimental setups. And we'll come back to that in a little bit. In terms of critique, one thing that really stands out to me is the DSL they've decided on for users to use when determining relevance criteria. So you can see there are these keywords like less and more, there's most, least. These are a little strange. I'd rather see criteria defined numerically. These sort of keywords don't really have much place in programming, in my opinion. And the other thing is that there are some questions around how well the system scales up. So with respect to that Shopweiser application, the authors have indicated that the performance of this monitoring approach is compromised when the software system is sufficiently large because there's much more there are more methods to collect stats on and sort and score and etc. So it would be interesting to see how this performs on a truly large system. But aside from that, I actually really like this approach. I think it makes a lot of sense to automatically try and determine where the monitoring should occur as opposed to putting all of that burden on the programmer. This is quite a nice approach in my opinion.